Yeah, so I will, well, talk about scientific visualization. So I think the title was about 10 simple rules for better figures. I will go over the rules. So this came from an article I wrote some years ago about it was for biology and plus computational biology. So I will just go through the rule. And maybe before I will talk generally about scientific visualization. So I guess you're all familiar with scientific visualization. Oh, doesn't work. But well, first thing is that to understand the importance of vision when we look at some information. So if you, because I'm working in neuroscience, so I know this data, but almost 50% of our cortex is dedicated to visual processing, and so that's really a huge part of the cortex. So in our case, this is occipital occipital cortex, and because of that, it has well impact on how you process information. So this is one very well-known example. So I don't know if you know it. It's called ANSCOMBE'S QUARTET because it has been done by a QUARTET and by ANSCOMB, sorry. So here on the screen you have a 4 series. So they are labeled 1, 2, 3, 4. And if you look at the series, they are made of X and Y numbers. And now what is interesting is that if you take the mean of X for all the series, this is equal to 9. If you take the variance, this is 11. If you take the same for Y, and mean and variance are also the same, you can do a linear regression with you got this specific line with a R squared and p-value, and everything is the same. And so naturally, if you look only at those figures, you would say, oh, okay, so those are the same series. And now if you draw a representation of those same series, then you can see this is quite different. And then immediately you can see that they are different. So maybe the first one is what we expect. So you have some data spread over a line. The second one is, well, you can, of course, you can do a linear regression, but it doesn't really make sense in that case. And the two other cases is a Y outlier case and the X outlier case. And of course, if you look at only at the numerical data, it's really hard to find that. And if you do a quick figure, then you immediately see the difference between the series. So it means that the scientific visualization, of course, you can use it for a scientific article to explain something, but this is also really something important when you investigate data. And one of the first case of using visualization for while finding information, it's made by John Snow, which is considered as wrote the father of modern epidemiology. And in this case, he was trying to find the source of a cholera outbreak in London. And so what he did is that he has all the different cases of death in some area of London. And what he did, he plotted the place of each death. And so on this original map, this is a black square on the map, but we can translate this map in using Google Maps some 100 years later. And so here the deaths are, sorry, the small yellow disc, and the blue pin are the whale at that time. And what you can see immediately again is that at the center of all the deaths, you have a specific whale, and this was the whale that was infected. So again, it's one of the first cases when you just use visualization to find the information. And more generally, so visualization, as it has been defined by the NSF a long time ago, but mostly it says that visualization is a method of computing. This is really one way to consider visualization. It's a different way of computing, and you use the visual part to extract the results. And so how do you compute for visualization? Well, you have what is called the visualization pipeline. So if you had ever done a figure you have been doing this pipeline, even if you don't know it, but mostly it starts with your raw data. It can be just, well, anything. And maybe one of the first things to do is to select the data you want to show, and possibly to do some analytics, like, I don't know, extracting the mean, the variance, or any other processes. Because you need first to select the data, because of course you can have a lot of data from your research or for your work, and so you cannot put everything on the screen or in an article. So you need to select the data. Then you have to decide how to map the data to some figures, and I will show you some example later. But mostly, let's say you have, I don't know, X and Y coordinate for some quantity. You can decide, oh, I want to do a scatter plot, or maybe you want to use a line plot. So again, you have to choose what kind of mapping you want to do between your data and the actual plot. Then you have the rendering, and for the rendering, you have also to decide of other things, like what color do I want to use? How do I map a point to the figure? Do I need to tweak the size of the point, etc. And then finally, you have the display. And from that, so either you are satisfied with your figure, or you will interact with your with the figure. You can change the scale, you can change a lot of stuff. And then you will go back to either the selection, mapping, or rendering, and you will iterate until you get the final figure. So it's, well, at least from my experience, it's very rare that you do a figure and immediately you're satisfied with the figure. It's always back and forth with tweaking either the data because you selected the wrong data, or you need to apply a different filter, etc. But it's an iterative process, and hopefully at the end you're satisfied with the result. And to do that, I won't go into big detail, but at least when you choose the kind of figure you want to do, you have to consider what kind of data you have. And traditionally, you distinguish between quantitative data and qualitative data, because they will be mapped to different type of plot. And so I put some example, like a temperature for continuous data, or number of inhabitants for discrete. And then for the qualitative, it can be, for example, nationality, month, age group. So you can have some order relation between the data, but for example, for nationality, you don't have any natural order. So it means when you will plot the data, it's a bit different. So it's good to know this kind of thing. And then to do a figure, mostly what you do in the end is to plot some elementary items. So for example, you have points, marker, lines, areas, and with that you can set the position, color, shape, size, etc. Then you have the helper, like text, axis, sticks, and you can have interaction and animation. But the point is that if you, for example, if you know how to draw points, marker, line, and areas, you can plot any figures. But today we have a lot of different software, of course, because we don't want to write a script to give, oh, I want to plot a point here and another here, and I put a letter here. So we have more and more elaborated libraries that allows you to do that semi-automatically. And for some libraries, it can be fully automatic. But even with that, the question is thus how to organize and link this to underlying data. And another thing, so I speak about the sense of vision in primate, and especially in us. And it's good also to know a bit of psychology and neuroscience. And one important theory is called the Gestalt theory. And it's a theory explaining how you perceive things on the visual aspect. And there are a lot of different things, but I only, well, I didn't make the figure. I should put the reference. I forgot the reference, but it's a good illustration of the Gestalt principle. So for example, if I told you that if you see the vertical bar on the S, maybe you will say yes. But now, if you observe this lookalike bar, it's not really a bar. It's made of two shapes that are cut by the S. But of course, you consider this to be a single bar, and so you will complete the occluded part, and you will interpret this as a bar. The same for E, the letter E. So it's made of small dots. So you could also consider this as a small dots, but what you see really is a letter E. And if you look at the J, it's made of 3 different parts. But again, it's fine. You will see the J. So this theory is important to know that it exists, just because it means that the way you will design a figure and the way it will be perceived can be a bit different, because this will act on the perception of the figure. And it can be important for some very specific things. For example, when you want to compare some quantities, so you can have different ways of doing that. And on this figure from a nice book by Tara MUNZNER, here you can see different way of comparing quantity. So the first one, which is a position on the common scale, is probably the best, because you have the bounds and you see the dots that represent how far we are on one side or the other. If you go on the bottom part of the slide, if you use volume in 3D, this is the worst you can do. It's very, very difficult to appreciate the difference between the quantity between different volume. And the same is true for curvature. It's really difficult to compare. So it means that, for example, if you want to, if you need to do a plot with a scale comparison, maybe the first one is the best. And well, also the color luminance and saturation, it's also very difficult. So now if we go back to the different plots, there are some nice tools online. One is called the Data Visualization Catalog. And you have mostly the website is like this. You have this small plots. And for each of them, you can click, you get the source in different languages, in R, in Python, in Excel, Matlab, or whatever. And you have also an explanation of what is the meaning. So I guess for open planetary, maybe you have some specific plots that I use all the time. So generally, a plot, given domain of science will use this kind of plot and not the or other plots. So mostly you probably will find it. For example, in neuroscience, we use an event plot for representing neural spikes. So again, this is really a good site. So now from all of this, I can give you some advice. So again, this is from an article published in 2014. I think it's open access, so you can find it if you type the title, and you have also the explanation. And well, so the first rule is that when you make a figure, you have to ask yourself for who you are doing the figure. So I mean that if you are doing the figure for yourself, it's fine to just do a quick figure with without any quality, as long as you can see the information. So as for example in the ANSCOMBE'S QUARTET, the point is to show just a dot, and it's fine, you can see the information. But if you're preparing a figure for, let's say, a scientific article, or if you prepare a figure for lesson with your students, or if this is for, I don't know, public dissemination or to be published in a newspaper, you won't produce the same figure. So it means you won't put the same level of detail. So on the screen, this is one figure that has been published in a New York Times to talk mostly about the leading cause of cancer death. I think, so this is a remake I did with Matplotlib. So I think it's fine for a newspaper, but probably for a scientific article, you would need to rework the figure, because not all the information is present, and it might be difficult to For example, if you want to compare the cancer in men, it's a bit difficult to read. So it's fine for a newspaper if you want to make the main point that breast cancer is the main cause for women and prostate for men, but else you will need to work a bit on the figure. The second rule is to identify your message. So the point is that if you are making a figure, what do you want to show in your figure? So generally, you're making a figure because it will be too long or too cumbersome to explain everything with text. But then when you're making the figure, it's not for the pleasure of making a figure. The idea is really to show what is the main message. So here, this is an example I use in an article. So this was to describe the projection from the retina to some part of the brain, which is called the superior colliculus. And you have some kind of big deformation of the retina. So mostly it explains that at the center of your retina, it's only 2-degree aperture, you have the highest resolution, and as long as you go further away from the center of the retina, the resolution decreases. So this is illustrated with in this case, with a checkerboard that will never be projected like this in the retina, but it makes a point to show the actual deformation. And if you want the 2 degrees, so if you take your arm and you put an apple at this is where you are really seeing properly, and apart from this area, you don't have such a good resolution. But the brain gives you the illusion that you have a good resolution. The rule 3, maybe this is one of the most difficult, is the idea is to adapt the figure depending on where the figure will be seen. So, for example, if you do a figure for a scientific article, it's fine to have a lot of detail, as it is the case for the left figure, because when the figure is published in a scientific article, generally there is only one reader, well, one reader at a time, and this reader will have plenty of time to look at your figure, to look at all the detail, to read the caption, etc. Now, if you are doing a figure for an oral presentation, then the reader, the viewer, will only have like maybe 30 seconds to 1 minute to look at your figure. So this means he won't have time to look at all the details. And quite often, people will extract the figure from the journal and put it online and say, as you can see, and well, generally you cannot really see because there are way too much information when you look at the figure for only 30 seconds. Of course, it's more work to do a new figure for an oral presentation, but here, this is one example. So you have the original figure on the left that would be published in a paper, and on the right, I remove a lot of the different trajectories. I put a dash line just to be able to say, oh, look at the dash line, and I increase the starting point. So this is a very small simulation of a dual particle system, and depending on the origin of the starting point, you will end up in the top right corner or on the top left corner or bottom right corner. So the point is to show that this on the red is showing the trajectory. So again, this is a bit more work to do it, but it will make the message more easier to understand. Rule 4 is, captions are not optional. So, depending on your domain, it can be either you have a very long caption explaining everything, but in some paper you will have a very useless caption. So this is a case, for example, on the left, where I wrote, this was supposed to be the caption, oh, this is an optical illusion. And if you don't know this optical illusion, it may be hard to realize that where is the optical illusion. And so it's written on the right that the color of A and B are the same. And this is really the same. If you don't trust me, look for checkerboard illusion on Google, and you will find the image, and then you can check, because it's really, really surprising. Again, this is how we perceive things. So captions are really quite important. Rule 5 is do not trust the default. So if you are producing figures, mostly you are either using a software or libraries. And those software or library come with a set of default, because when you want to, let's say, plot a sine and cosine, the library has to decide a lot of things for you. So either it decides for you, or you have to specify everything. And when I say everything, it means, for example, on the left, you have to decide on the thickness of the line, the color of the line. You have to decide if you want to have a box around. You have to decide if you want the ticks. What are the labels for the ticks? What are the position of the ticks? What is the font family of the ticks? Well, really a lot of things. And if you look at a figure, usually you can guess what is the software that has been used between Matplotlib or R or MATLAB or Excel. Well, Excel is easy, because most of the time it's a bit ugly. So here, this is an example with Matplotlib, and you have the default one on the left, and with some tweak, you can end up with the one on the right. So it's only a matter of modifying some of the default to improve a little bit your figure. So with experience, it's not so hard to do it, but well, you can also lose a lot of time doing this kind of tweaking. Rule 6 is one quite, and well, maybe the most important, is to use color effectively. And there were a lot of problems with MATLAB, Matplotlib, and GNUplot, because the default color mat was a very bad one. So for MATLAB, it was a rainbow color mat. No, it was jet. No, it was a rainbow color map. For Matplotlib, it was a jet color map. For GNUplot, I don't remember the name. And you can see on the left that if you use well, the bad color map, then it will hide information. And so when you choose a color map, so first, don't use rainbow or jet. You have 3 different kinds of color map, which are called qualitative, diverging, and sequential. Sequential means that it's well, a sequential continuous value, while diverging is almost the same, but generally you have, let's say, negative. We have 2 domains. Like most of the time, this is negative domain and positive domain. Like, for example, for temperature, you want to represent the negative temperature in blue and the positive in red. In this, on the figure, here we have a signal with an increasing frequency. And in this case, this is only positive value. So you want to use a sequential color map like the purple one. And if you look at the high frequency domain, you can see that we are able to see the signal in this high frequency. Now, if you look back to the rainbow color map, you can see this is much more difficult to see the information. And the same is true for the seismic. So again, you have to, depending on the nature of your data, you have to choose the right color map. And then the actual color of, if you choose for a sequential, as long as it is sequential, it's fine. And then you can decide if you want to use a purple one or the blue one. And well, it's only a matter of taste at this point. So this is another illustration of why the jet is bad. So here you have Mona Lisa, the original color on the left. We can translate it in gray level. And then if I use a jet color map, you will see this red area that are really salient in the image, but for no reason. And what you can do instead, if you can use a Viridis color map, which is the default color map in Matplotlib. And here the picture is now much more uniform. So it means it doesn't attract your attention on some specific part for only a perceptive reason. Now, if you have something very specific with in your data, you will still be able to see it with a Viridis. Rule 7 is, well, maybe this one is not so easy to do, but the idea is to not mislead the reader. So in science, it's not supposed to be the case, but still you can have some problem if you don't know the detail of the library. So maybe first I will speak on the example on the right. This is something that is very well known, especially in, I would say, in politics and a newspaper. So depending on the message you want to convey, you can tweak the data. So in this case, this is the two same series. And in the top right, it is a series using the full axis. So it goes from 0 to value around 90, and but we represent the data using the full range. And of course, what I did on the bottom in red is that I cut the axis, and so now I'm representing the data from between 80 and 100. And of course, it will increase the difference between the data. And depending on what you want, the story you want to tell, you will use one or the other. Usually, for scientific figure, you will never use the bottom one unless you have a very specific reason and you have to give a big warning why you did that. The other case is more interesting because, for example, if you do a scatter plot, and let's say so scatter plot means you put a disk everywhere. And let's say you have a third dimension in your scatter. So you have X, Y, and Z, and you want to use a Z to size the disk. So instead of having only the point with the same size, you use a Z coordinate to size the points. And then you have to know if your library will use this Z coordinate for the radius or for the areas. So here you have the quantity that are represented are 4, 3, 2, 1. On the top, I use the area of the disk, and on the bottom, I use the radius. And you can see the perception is quite different. And the best is to use the area because from a perceptual point of view, I think it's easier to see that the relation is 4, 3 to 1, because now if you look at the bottom part, if you want to compare the right disk to the fourth disk to the first one, maybe it's hard to say the relationship is only 4 to 1. You naturally interpret the area of the disk. And those kind of trick I use already every time. So for example, well, the pie chart also is a bad idea, and in this case it's even worse because it managed to have a 50% that is not half of the disk, which is kind of surprising. I'm not even sure how you can end up with such graphic. If you look at the top left graphic, I can use my cursor. So this was a poll for the election in the UK. It was 2 or 3 years ago. And if you look at the representation of between the numbers and the area, it's well, totally arbitrary. So for example, here you have UKIP at 0, but still they appear here when it's really 0. If you look at this, which is supposed to be 34, and this to be 14, and if you compare the two areas, they are approximately the same size. So it's, I don't know, it's this graphic is a total crap. And we have another case. This time it was in France on the national channel, and here they really tweak. Not only did they cut the bar, but they really change the representation of the result. And this was for the presidential election. So if you look here, the difference is supposed to be 2.5, and here the difference is supposed to be 5. So there is something really wrong with this graphic. And why they did that? Because he wanted to tell a story about these 3 candidates, but not this one. So again, this is totally wrong to do something like that, but there were no consequences. Rule 8 is avoid chart junk. So maybe you produced some long time ago. Did you ever produce graphic like on the left? Maybe some of you did. But we can go over what is wrong with, with this graphic, but pretty much everything is wrong. So first, there are too many plots on the same figure, and it's really hard to see, to follow just one signal. You have also a yellow background for no obvious reason. You have a grid that is not aligned with the data. You have far too many labels, and you have also the legend that covers the signal. So for example, maybe there is something really interesting in here, but you will never know because you just put your legend on top of it. So an alternative is to have to split the signal and to have one seq line for one series, and you only put the other in the back. And I think with a pandemic situation, we got a lot of those kind of graphic. And what is interesting is that if you look at the area of the two graphics, it takes the same area, so you don't lose a space by doing that, and it's much more easier to look at to compare the data. Another thing is that it's not always a good idea to put too many stuff on your figure. So here, this is one example. So a long time ago, let's say 10 years, using Excel, you could end up with those kind of graphic. And well, again, there are way too much information. So maybe I can show you the animation if it works. Can you see it? Can you
yes,
see
we can see it. Yes.
Okay. So here this is just a remake of animation by Dark Horse Analytics, and this show how you can remove all the redundant information and all the unnecessary information. And so you start with a figure with way too many things, and in the end you get a very clean graphic with only the main message that is shown. So here you see we remove a lot of things, and this is a final graphic. If you compare with the first one, it's much easier to see the information. And rule 9 is, well, I talk about the message, and of course, the message is the most important. So even if your figure is not so clean, it's fine as long as you can convey the main point. So we saw that with the ANSCOMBE quartet, and here this is another example. So it's one illustration of what is called the uncanny valley for in robotics. And so the idea is that if your robot is industrial or a bit humanoid, but not too much, it's fine for people. They will accept the robot. And that's after some level of realism in your robot, people will find your robot to be a bit creepy. And after that, it's fine. So the idea is really to show this this uncanny valley because it's not really based on any data. And to do that, I just use the XKCD filter. So I guess you know the XKCD comics. So in Matplotlib, when you do a figure, you can apply XKCD filter and you end up with something like this. But it might be a bit difficult to publish in a scientific journal, but it's yeah, it's a lot of fun. And last rule is to get the right tool. So one thing is that when you are comfortable with a library or software, maybe you want to use this library or software to do just everything with it. But there are also some dedicated tools that can just make your life easier without well, pushing your software to the limit. So I list only a few of them, but well, one that I use all the time is called PDF crop. And let's say you make a figure and you have this white area around your figure and you want to get rid of them. Well, you have a PDF crop. Its only goal in life is to just do that, to remove the white border on your figure. And so it means that if you insert your figure in an article, it will really take the full area to display your figure. GraphViz is also something that if you, let's say you want to do a graphic with a box and arrows, so you want to have something that is linked to another thing that is linked to another thing. GraphViz can do that with so the input is let's say you want to have A with in a box in a circle, an arrow to B in a circle. You write A minus greater B. So minus greater is to do an arrow, and then you got directly the graphic. You can do that with 2 nodes, but you can also do it with 1,000 of nodes, and it will do that automatically. So it might be also something useful. Image magic is for if you want to transform a bitmap image. You have all kind of script to do that for pretty much anything you can think of. Then you have GIMP and Inkscape for either bitmap image manipulation or vector image manipulation. And well, the idea is that you have really a lot of tools around that can make your life simpler. By the way, I have no idea how long I've been speaking, but it's not too long from now. But...
Not too long, 40 minutes.
Oh, okay, I'm almost done. Yeah, so talking about the tools, so because we're talking about Python, so this is a kind of a view of the Python ecosystem. So at the center, you have, well, Matplotlib. And if you're not comfortable with Matplotlib, you can also use other libraries that are more automatic, for example, like Seaborn, but you have a lot of other libraries. For example, if you have a network X, if you're working with a network. Now, if you are in a 3D, and I guess maybe for OpenPlanetary, it might be important, you have also OpenGL and you have a lot of other library around. If you want to go on web, then you have also some things to go from, let's say, Matplotlib up to the web through. For example, you can use Bokeh. No, Bokeh, it's directly onto the web into the Jupyter notebook. And you have a lot of tools like this. One that is interesting when you have really a lot of data is a data shader that allows you to manipulate billions of data in a very efficiently. Just a note about format. It's good to know that there are different formats. Maybe you are used to it, but if you have the opportunity to save your figure in a PDF or SVG, it's always better because it means you can zoom at an infinite level. When you have too much data, maybe it's faster and easier to use a bitmap format, but then if you have to choose, it's better to use PNG because it's a lossless format. So when you are doing a scientific figure, it's best to have a lossless format because if you use JPEG, it means you lose some information. But it's not that important information because a JPEG format is intelligent enough to only remove the unnecessary, well, not unnecessary, but it won't make a big difference in your in the output. But if you can choose a PNG. And yeah, this is another examples. So we started with ANSCOMBE'S QUARTET. And this is a kind of thing you can do with a data shader. I think Todd Schneider used something else. What is interesting, if you look at so this is a blog post quite long, and it shows you how to use the data and to produce some stunning figures. So here, this is all the individual taxi trips and Uber in from January 2009 and 2015. And you can see, you can recognize New York with Manhattan and the different airports, of course, because you take a lot of a taxi. So again, only with one figure, you already learn a lot. And I will stop here. So this is some resources you can find online. So, one error. So this is the book Chase was talking about. So it's online also, it's free. You can buy it at Amazon if you want a printed version, or you can even print your own version because the sources are online. So actually, you can there's everything to print the book if you want. This one is also online. It's really good, and it's open access. And those are also good, but you have to pay to one. And yeah, Tufte is one very well known in visualization. He did many books that are really appreciated by a lot of people. And then you have other resources. So if you're interested, one is a nice data is beautiful on Reddit. You have stunning graphics, and this one is funny. It's one of the worst graphic you can produce. And this one is about D3GS, which is a JavaScript library to do a lot of visualization online, which is very popular. I will stop here. Maybe I've talked too much. If you have any question,